The second part of this lab activity is the synthesis of aspirin. We won't be actually doing the synthesis this semester, obviously, but we could take a quick look at the procedure. It involves having a flask to which we add salicylic acid, and we measure that accurately so that we can determine the theoretical yield. And then we add the other reactant, acetic anhydride, and it's about 3 milliliters of that. But we know with these quantities that salicylic acid is going to be a limiting reagent, so we don't have to be too accurate with the acetic anhydride quantity. Sulfuric acid is a catalyst that has to be added as well. The reactants are mixed, and a stopper with a hole in it is added to try to prevent condensation of moisture entering the flask, because that can destroy the acetic anhydride. The flask is then boiled for 15 minutes and then removed from the hot water bath, and the reaction is quenched by adding ice water, and this then destroys the acetic anhydride so that the workup can produce a pure product. The flask is then cooled, and crystals form, and these are broken up with a stirring rod. The crystals are collected on a Buchner funnel and rinsed with cold water so as not to dissolve crystals or minimize how much are dissolved as they're rinsed. And then these are air dried. And normally we would hold on to these crystals for a week, and the next week we would measure the yield when the crystals are dry and test the aspirin for purity. So what about the reaction? Well, the reaction is between salicylic acid and acetic anhydride with an acid catalyst. And salicylic acid itself is known to be an analgesic. It can relieve pain. It's been known since ancient times, but it can cause irritation in the gut. And so in the 1890s, the Bayer Company produced aspirin, which is a derivative of salicylic acid. You notice in salicylic acid, it's a phenol. There's also a carboxylic acid on here, but the phenol functional group is converted upon reaction with acetic anhydride. If you look here, this is an ester. An ester looks like a carboxylic acid, but instead of OH, it's OC. So it's a carbonyl and an oxygen attached to the carbonyl carbon, and instead of a hydrogen, which would make it a carboxylic acid, it is an ester. So you see the ester by looking at the side of the molecule to which we've added to the salicylic acid. There's a lot of history that you can look into. It's kind of interesting. Within Bayer itself, a lot of scientists were fighting over who deserved the credit for the synthesis. And should be noted, Bayer had a lot of products. Some of them are no longer available at your local pharmacy. Apparently they used heroin. They sold that for children who were teething. They would say to rub that on the gums and it would help. There's also, you can look up on, say, Wikipedia or look up on the internet, the Great Phenol Plot. Back at the start of World War I, the U.S. was not yet in the war, and but there was sympathy growing for the Allies versus Germany, although some people still wanted to support Germany. And phenol, which is the starting point for the synthesis of aspirin, we're starting at salicylic acid, but in industry, you start with phenol, make salicylic acid, and then aspirin. Phenol is also used for explosives, trinitrophenol. And so the British were using that up, and Bayer and other companies that use phenol could not get their hands on it. Bayer had a problem because they're a German company. Another company that needed it was Thomas Edison's company for his manufacturing of phonographic records. And he set up a plant to manufacture phenol for his own purposes, and then started selling it because the price went way up. And it turns out that the Germans set up a front company disguising themselves in the U.S. to buy up phenol. And so Thomas Edison was all embarrassed by that. That it turned out he was selling to the Germans when the U.S. was getting close to joining the war. This reaction, you can think of it, if you recall from Gen Chem, as a double replacement reaction. So that's where A and B, C and D, it's kind of like the trade partners. So now it's A and D, and B and C are partners. So salicylic acid, it's the whole molecule except for that one hydrogen on the phenol is A and B. And then acetic anhydride, you can see the division of that molecule, and the two halves switch partners, and you get aspirin and acetic acid. In organic chemistry, we look at this as a nucleophilic acyl substitution. So here's our acyl group where you have a carbonyl, and this is a leaving group. So when you look at acetic anhydride, here's our acyl group, and all of this is our leaving group. So from the perspective of that acyl group, we're replacing the leaving group with basically salicylic acid minus the hydrogen. So that's an nucleophilic acyl substitution. So the reaction is acid catalyzed. We'll look at the mechanism later. But you can use phosphoric or sulfuric acids. Phosphoric acid is a little bit better, but sulfuric acid works fine. The reason we use these is because you can obtain these in very concentrated solutions, and you don't want a lot of water around. And if you have a dilute solution, of course, there's more water, and that will destroy the acetic anhydride. Sulfuric acid can react with the aromatic ring, electrophilic aromatic substitution reaction. So phosphoric acid's a little bit better, but it doesn't seem to be a problem. It works fine when you synthesize aspirin with sulfuric. At the end of the experiment, we do a ferric chloride test, iron 3 chloride. So what does that test for? It tests for phenols. And which product or reactant would test positive? Well, here's our phenol in salicylic acid. So salicylic acid has a phenol in it, and that should test positive. So what does a positive test tell you? Well, the aspirin is not pure. So if you've synthesized aspirin and you do a ferric chloride test, if it's pure aspirin, you should not get a positive test because there should be no phenol. If you do get a positive test, then there's some of the starting material, the salicylic acid there. Salicylic acid is the most likely impurity in the aspirin. The acetic anhydride gets destroyed by water during the procedure at the end when we quench the reaction, and it forms acetic acid, and that's water soluble and should wash away.